now solving the problem that we set up in the last video. Alright, and again, we will always do this graphically. Alright, so we'll graph the system of linear equalities, which is what we practiced in 5.1. So it's the solving this system. This is the one that I've had graphed. So I've graphed this using, again, my graphing tool and pasted it in here. And since we've already kind of gone over that, I'm just going to, this is, if you're following along and you want to do this on your own, again, graph those like we did in the last video in 5.1. Shade above for both of them. You do have to make your window a little bigger if you want to. Again, you don't have to. You can just look at the notes here. Alright, but here are my two equations. So, the first equation, here, this red one, this is my x plus y equals 65. And then the green equation here is the 4x plus 5y equals 300. Apparently that didn't come over. And I didn't shade it in, but remember, this is also not included. Everything down here is not included. Right? So only the... So remember, this is the less than y. So it's just everything in the first quadrant. There it is. These are also all the false parts. This is all false over here. Alright, so this is the feasible region. This is the solution set. Everything bounded on this sort of it's not quite a triangle because it's sort of got a bent spot here. So it's kind of triangular. I can't draw a straight line today, apparently. But it's this open spot here. Alright, everything here. And I've already marked off the corner points. So my corner point A was up here at 0, 60. My corner point B is where the two lines intersect, and that's at the point 25, 40. My corner point B here is at 65, 0, and then there is this corner point at the origin, right, because this is the side, this is the side, where it goes through the y-axis and the x-axis, right? The x-axis would be the y equals 0. The y-axis is the x equals 0 linear inequality. Right? And so then we write them in a table to solve the problem. Alright, so we've got the A, B's, and C's, and those are remember, in order to be a corner point, they have to go through at least two of my equations in my setup. Two of my equations. Alright, they have to go through two of my lines represented in my system, my linear inequality system. And so here's sort of the table that we talked about at the end of 5.1, and there's the coordinates that go with them, the ones that I listed on the graph. Right, these corner points are going to become important. This is sort of the theory. So like I said, this video is basically the theory behind how things work and what it is that you have here, which is why I said at the end of the last video, this is one of those that if you wanted to, you probably could skip and you won't miss anything. But if you're curious on the how and the why things work and the answer to the question, then I'd encourage you to watch the video. Right, so to determine the optimum value of the objective function on a feasible region. And so the feasible region is just the fancy way the linear programming people who set it up, that's our solution set. That's that region here. This empty area is the feasible region. This is the feasible region. Alright, the solution. So it's just, again, people who come up with these things decide to use their own terminology for stuff, and that's it. So that feasible region is just the solution set for this particular application. Alright, so to understand how this works, again, we're going to look at some investigating. We're going to talk about what the feasible region means, what the corner points mean, and how we get to our optimum value. Again, this is the theory behind the theorem we're going to get to. So this is the trying to get you to understand the theorem when we walk through this example. Understand what feasible region is. Understand what that area is and what it means in terms of the problem. Right, so remember, our goal is to optimize revenue, which was the 25x plus 30y. So we want to find the point that lands in the feasible region within our constraints. Again, the feasible region is just the solution set, which would be the area in the middle that's unshaded and all of my edges that make up that area. Alright, so we need something from within our feasible region, within our solution set, that makes our revenue as big as possible. Alright, so we're going to look at this and sort of get you to hopefully understand what that feasible region is. So maximizing the revenue in our feasible region. So the first thing is, well, understanding what the feasible region is, the solution set is. So my first question is it possible to have a revenue of $900? Is it possible? It's all the question is. Can Tom have enough canoes and kayaks to generate a revenue of $900? Well, again, we're investigating. And so I'm going to let my revenue equal 900. So that's what we do. We set our revenue equation equal to 900. And then I'm going to graph it, right? This is the revenue equation set equal to 900. And then I solve for y so I could graph it on my calculator. Right? That's all I did. Solve for y so that we could graph this. All right, so add the line to my previous graph. All right, and again, it's only in the first quadrant because that's all we want. And so when I go to graph this is in your notes. This is the graph. So that purple line is the graph that represents so any point on that purple line, right? Any point on that purple line represents a revenue of $900. So I pick any point off that line. I pick a point here, which looks to be like it's, I pick the point, not 535. All right. That would mean that should give me out a revenue of 900. Right? And if I pick any point on this line, any point on the line, it will give me a revenue of 900. And so the answer to my first question is, which I wrote again down here, is it possible, is it feasible to get a revenue of 900 within our feasible region? Yes. There are points that exist in our feasible region that have and then any of these points will make this true. So that's yes. All right. Now, my second question is that the biggest revenue I can get? Well, it's kind of in the middle of my line here, so I'm going to guess there are bigger revenues out here because there's this more area here. And so I'm going to assume that no, that's not the biggest revenue I could get. Alright, so what I'm going to do is I'm going to do a little more investigating. Alright, so I pick a few more revenues. That's all I'm doing is investigating. So I picked a few more revenues to graph. So I did a revenue of $1,500, a revenue of $1,800, a revenue of $2,100. And so I did the same process. So my revenue equation, I set each of those. And then in order to graph them, I have to solve for y. So this first one, again, this is just if you want to graph. This is what I did to get the graph. If you want to do it on your own and practice on the calculator, you can, although you don't have to. But this is what I did. All right, so I graphed each one of these, which represents, the first one represents a revenue of $1,500. This represents a revenue of $1,800. This represents a revenue, and I did them in different colors. So I'm going to go to the graph now. All right, and they're labeled on yours as well. And I did them as dotted lines so that you could see the difference. So I still left the purple line there. That was my $900 revenue. This sort of darker green is my $1,500 revenue. So any point on that dark green dotted line, I can get $1,500 revenue is. Then I have this sort of lime green one. If I'm on any point on that line, the revenue generated would be $1,800. And then the last one is a revenue in this blue color. That blue dashed line, the dark blue there, represents a revenue. So those would be any point on that line would give me X and Y values that would generate a revenue of $2,100. Alright, so my first question is, can I get each one of those revenues? Can I get a revenue of $1,500? Well, yes, I can have a revenue of $1,500 because it lands in my feasible region. Can I get a revenue of $1,800? Well, it does look like it's kind of on the edge here, and there might be some spots in my feasible region here. Although down here, this is outside my feasible region, so all of these points that land here in the shaded area, even though they're on my line, I can't use. All right, I can only use these here, but there looks like there are some there. So I would say yes, there are few, but there are some that seem to land in the 1,800 region. What about the 2,100? All right, this blue line. All right, the blue line exists, but it exists where? It exists in all the false statements, which means it doesn't land in my solution set. And so it's impossible to get a revenue of 2,100. And so, yes, we can get a revenue of 1,500. Yes, I can get a revenue of 1,800. not very many of them, but I can. No, I cannot get a revenue of 2100. It's not in my solution set, not in my feasible region. There are no points that exist within my constraints, exist within my inequalities, within my budget. Remember, my constraints are my budget and my number of boats I can have in my garage or wherever I keep them. So I can't have enough, I can't buy enough boats to then rent in order to make a revenue. So case 4 does not exist. There are no points on this blue line that land within my budget and the number of canoes I can have. All right, don't land in my feasible region. All right, so based on this, and based on that fact that that green line is close to my edge, 1800 is starting to get close to, and it actually is fairly close to what the actual number is, the maximum. All right, if you ever go on and you do these linear programmings in higher level, I think it's microeconomics or one of those classes, don't quote me on that, but some type of economic class to do these, and we won't do anything with ISOs, but if you do go on to some higher level economics classes, they talk about ISO revenues, ISO profits, ISO costs, and other ISO functions. And so those lines that I just drew, for your FYI, for your information, nothing to do with this class, but just so that you're aware of what they are, so it's always important to know what things are. Those are what are called ISO lines. So I drew ISO revenues. All right, they're all parallel. You look at them. In case you didn't notice, every single one of these have the exact same slope. What changes is the y-intercept. And so whenever I find a revenue, they're all parallel. If you look here, every single one of those ISO revenues are parallel. And so ISO revenue, and what we want to do is we want to find the ISO revenue that makes the largest revenue that still falls within the feasible region, which again is our solution set. Right? And again, based on those lines, can we guess? Well, it's not really necessarily easiest to guess. What it turns out is the reason why we ask you to practice finding corner points is we're leading up to this theorem, is there's a special ISO revenue that connects with one or more of my corner points, and those ISO revenues are where we get our possible maxes and our possible mins. So when our revenue intersects with a corner point, those revenues will give us our optimum value. Right, in this case, it was the corner point 2540. All right, so it turns out the feasible region with the largest revenue occurs at the corner point 2540. All right, and again, that is what we're going to do. All right, so it comes from the fact that, and we can kind of see that that's where it's going. If you look at the 1800, it looks like it almost lands right on. And remember, it intersects sometime around here. And so it was a little bit bigger than 1800 where it actually intersects that corner point. There would be another line at that value and it intersect this corner point. At that corner point where it would intersect, which is the 2540, that will give us our biggest possible revenue. And so the answer to this is the corner point, and the corner point's part of the feasible region, gives us our optimum value. So the optimum value is, if we have 25 canoes and 40 kayaks, right, when we generate revenue, it'll give us the most revenue possible, which is 1825, which is really close to the 1800. And so that's the big, and that's it. That's it. We can't have infinitely many canoes, right? We can't have infinitely many kayaks. We're limited to our budget that we can buy and how many that we can have. And if you'll notice, this is the maximum, right? 65 was as many canoes and that's most of the cases. That's the way it will work out. Again, usually you optimize when you have your maximum, at least when you're looking for your biggest case. Now, it might not be the case when you're looking for your smallest, for low in cost or whatever. But you'll notice that the 25 and the 40 add up to the 65. Right? Again, that's as many boats as he can have. He can't have any more than that. And so that's the single biggest revenue possible. He cannot get a revenue based on his budget and the number of canoes and kayaks he can have. He cannot generate a bigger revenue than this. Right? 1825 if he has 25 canoes and 40 kayaks. All right. So that was sort of the theory behind what we're going to do. We're going to get to this theorem, which is what we're going to practice in the next set of videos. Alright, so this leads us again. This is sort of just where it all kind of comes from, and hopefully give you a little glean into understanding a little bit what a feasible region is. what we're going to do is the theorem. This is the theorem called linear programming theorem. The feasible region, remember, is just the solution set, bounded. Right, so again, this is the bounded case. And it's bounded usually because I know that x and y have to be positive in our applications. All right, so the optimum solution in these cases exist, they happen, and they only occur at the corner points. So what it comes down to us is, well, which corner point? And that's basically what we have to solve. So in order to find the optimum solution, you need to do is locate the corner points of my bounded feasible region of my solution set, the corner points of my solution set. And then there's more than one corner point. There's always going to be more than one. I don't know which one gives me my optimum solution. You can sometimes guess, but you should always check and make sure, because sometimes you get two. Substitute those into the objective, your revenue, your cost, your profit. Whatever value comes out the biggest is your max. Whatever value comes out the smallest is your min. All right, we'll give you your optimum value, and we'll practice that in the next set of videos.